So hi everyone, welcome to another linear integrated circuit class. In the previous class, we did some introduction on linear integrated circuits, different electrical elements, passive and active elements, diode, transistors, a little bit of introduction and history. Today, I'll continue with classifications of linear integrated and ICs in general, integrated circuits in general. Today we will finish the introduction of LIC, and next week we will start with ideal op-amp. So for the classification, as mentioned in the last class, there are different ways to classify ICs. The classification based on the active device, we have bipolar ICs and unipolar ICs. The classification based on the application, we have analog or linear ICs, which is the topic of this class, and digital ICs, which is a topic of another class, digital design. Classification based on the technology, we have monolithic technology, bipolar and unipolar, and we have hybrid technology. And the classification based on the number of transistors, we have SSI, MSI, LSI, VLSI, ULSI, and GSI. So classification are based of, according to their operational application, we have two main types. We have digital ICs and we have linear ICs. Linear ICs are also called analog ICs. Anything that could process a analog signal, analog meaning a continuous signal, is an linear integrated circuits. These analog signals, linear signals, are usually used in audio amplification, signal processing, and so on. Usually on top of these ICs, we have to add other elements like capacitors, resistors. So we have, usually when you have a linear IC or analog IC, it's combined with other elements like a capacitor or a resistor to build different type of filters, for example. So imagine that you have an analog IC that does signal processing on an audio signal. The same thing that you have on the base of your on your car, and you can adjust that. And that is usually connected to a low pass filter or a high pass filter, and that is finally connected to a speaker. So for a low pass filter, for example, the simplest low pass filter looks something like this. And then we have the analog or linear IC connected to that. These ICs are usually used to amplify a signal, to filter out certain part of a signal. They're usually very, very cheap and low power. They were very popular like 20 years ago. Then with the rise of digital, they became less popular. Now they are gaining a lot of attention and becoming popular again. One example could be a voltage regulator. That's a good example of a linear integrated circuits. The thing that you learned already in electronics. So anything that deals with the digital signal, it's a part of a digital IC. Digital ICs usually do not require additional parts. The only thing that you need is to connect input, output, and a power supply. They are used to build logic circuits like anything that you see in a laptop, on your phone, computer, anything that is a digital signal. Nowadays, like 90% of all ICs are digital ICs. We can build different logic circuits like digital logic gates, and NOT gates, AND gates, NAND gate, OR gate, multiplexers, decoders, encoders, latches, memories, all of that could be built out of a digital IC. The output of an analog IC, as I mentioned, is continuous. It could get different values. The output of a digital IC, usually it's the logic of 1 or high and logic of 0. So we usually have two stages, high and low, or on and off, and 1 and 0. So that's the reason we call them digital, that it shows a certain digit. Usually the signal high or 1 represents a voltage, let's say 5 volts, and 0 volts shows 0 for a normal digital IC, like a 7400, which is a NOT gate. Analog digital ICs share properties common with both analog and digital ICs. Sometimes we have a combination of analog digital ICs. It's like a hybrid setup. Some analog ICs can have a digital component, like an analog IC with a digital counter. And it's the other way around. You may have a digital IC, but the input or output could be analog to be able to control a motor or get a data from a sensor. And then you have an analog to digital converter, or a digital to analog converter to convert analog to digital and digital to analog. These two are examples of digital and analog ICs. You can't determine by the shape or that if it's analog or digital. You have to look into their data sheet. This particular one, the left one is a digital one, and the right one is an analog. But again, they don't. When you look at them, you can't differentiate between analog and digital. They come in different packages, different pin numbers. But we have digital ICs that look like the right one, and analog one that look like the left one. Classification based on the structure and technology, we have monolithic. These monolithic ICs are the most common type. All the ICs that you see around you are monolithic. They are built on a single layer, or we call it substrates. The monolithic, it comes from the letter Greek meaning one stone. And the reason that we say one stone, because we build it on a single layer. It's like a printer that it prints on a paper. I have a video that I would show you. It's the exact same thing. We have a technology, there's a technology called a lithography. It basically uses lasers to carve in. It's like carving in on a stone. It's the same thing. We have it on but we have it on a silicon. Silicon, the reason that we have semiconductor is because we have semiconductor materials. Semiconductor materials are between insulators and conductors. They are mainly made out of silicon, which is technically sand. There is a process which we purify that sand. We build something called wafers, and wafers are these discs that later on we put them in the devices and we print on them. They are usually low power. For low power, like building an IC, CPU with GPU for iPhone. Therefore, they are preferred in low power applications. But they are extremely cheap, very fast, low power consumption, and you can build billions of transistors on a monolithic system. The next one is thick film. Thick film is basically when you want to add capacitors, resistors, you want to build a passive element in a circuit. We use thick film. Thick films are easy to produce, but they're expensive. They have a lot of applications. So we build them usually layer by layer on a glass or a ceramic base. They are used in a lot of power applications and filters and so on. But again, they are easy to produce, but with a great precision, but they are expensive. And finally, we have the hybrid ICs. Hybrid ICs, obviously, it's a combination between thick film and thin monolithic film. And when you want to build a hybrid IC, imagine that you have a DC component, AC component, and you want to build a power electronics. You can combine these and build a hybrid system, which covers a lot of applications. This is a classification of integrated circuits. The substrates, meaning the base that we print on and make the ICs on, it's like a printer. The substrate would be our paper. That could be made out of silicon, ceramic, glass, or even a combination of them. Monolithic ICs are made out of silicon. The structure are active and passive device analogs with interconnections on a single chip. BJT, which are bipolar junction transistors, and MOSFET or field effect transistors, metal oxide field effect transistors. These are made out of monolithic ICs, or all the ICs that you see around you, like digital analog, mainly are made out of monolithic ICs. Passive devices like diffuse resistors, oxide capacitors, MOS resistors, and so on. The application is for linear and digital IC. Thick film, you can read faster than I can. So they are made out of glass or ceramic for MOSFET transistors, for passive components, and they are usually used in digital ICs. And finally, hybrid is a combination of both of them. It's for BJT and MOSFET transistors made out of glass, ceramic, or silicon for passive and active devices, for linear and digital devices, like middle film resistors, cement resistors, oxide capacitors, and so on. This is a structural monolithic IC. These are in the range of like a few molecules, very, very thin. Thousands of millions of them could fit in a typical needle, very, very small. And the next one is going to be the VLSI ICs, which are the large scale ones. Now, I think that video would explain more because it has a lot of interesting graphics and explanation about that. And finally, we have thin, thick, and hybrid manufacturing as well, which I have a video for it. Let's go back.
This chip can take up to 26 weeks to make. In its as many as 100 layers, billions of transistors are packed into an area about the size of a fingernail. They're the brains behind almost everything we use in our increasingly electronic world. Here's how these complex, tiny devices are made. The process begins with silicon-rich sand. Why silicon? Silicon is a semiconductor. It's the sweet spot between an insulator and a pure conductor. That means its properties, such as its conductivity, can be altered by adding impurities or doping to meet the needs of different electronic devices. This also allows us to control the electrical signals that pass through. Silicon is also abundant. It's one of the 10 most common elements found on Earth. But much of the silicon found in the wild is chemically bound to oxygen, so the two elements must be separated. The sand is combined with carbon and melted in crucibles to produce carbon monoxide and 99% pure silicon. After further processing, ultra-pure silicon is produced. Next, a seed crystal is placed in contact with molten silicon. As the seed crystal is slowly pulled away, silicon atoms are deposited on the bottom surface. The result is a large cylindrical boule, or a single crystal ingot of pure silicon. The boule is then thinly sliced into wafers. Silicon wafers typically have diameters of 1 to 12 inches, with the most state-of-the-art facilities being able to produce wafers up to 18 inches in diameter. Bigger wafers are, of course, able to yield more microchips. Once the silicon wafers are cut, the production process begins in full. Microchips are made in extremely sterile conditions, free from contaminants such as dust. If even just one particle of dust makes its way onto a silicon wafer, the entire batch is at risk of being ruined. This would derail a process that can take an average of 12 weeks. The first step of the production process is deposition. A thin, non-conducting layer of silicon dioxide is grown or deposited on the surface of the wafer. Then the silicon wafer is prepared for lithography by coating it with photosensitive and light-resistant materials. The next step is very critical: exposure. The prepared silicon wafers enter a lithography machine and are exposed to UV light passed through a reticle containing the chip's blueprint. The areas exposed to light are hardened, while unexposed areas are then etched away by hot gases to leave a three-dimensional microchip. The electrical conductivity of different parts of the chip can also be altered by doping them with chemicals under heat and pressure. This process can be repeated hundreds of times for the same chip, producing a more complex integrated circuit at each step. To create conducting paths between the components, a thin layer of metal, such as aluminum, is overlaid onto the chip, and the etching process is used to remove everything except the thin conducting pathways. Several layers of conductors separated by glass insulators can be laid down. Each chip on the wafer is then tested for performance before it's separated from other chips on the wafer by a saw. Since microchips are essentially circuits built on an incredibly small scale, they have a basic set of components. Capacitors can temporarily store an electrical charge. Resistors help control the electrical current. Transistors can either amplify or switch the electrical signals passing through. For more advanced chips, like those found on high-end graphics cards, there can be upwards of 28 billion transistors on board. More transistors on microchips allow them to send out more instructions, increasing the computational power. Moore's law predicts that computer chip manufacturing would advance at a steady rate, allowing transistor counts to double every 2 years. Based on the sheer power of the technology we use on a day-to-day basis, this decades-old prediction seems to still be mostly true. Manufacturers have been shrinking down their transistor sizes to fit more on the chips. Each breakthrough in transistor size has allowed the production of more powerful chips for our phones, computers, and gaming consoles. In recent years, they've gotten each transistor down to as small as 8 times 10 to the power of -8 inches in diameter, allowing an amazing 50 billion transistors to be crammed onto a single chip. Manufacturing microchips is truly one of our most complex feats, and yet innovations are happening every day.
So the other classification that we have for integrated circuits is based on the size and how small and how many transistors we can fit on a chip. The first invention of the transistors from the history we already know, it's 1947. Development of silicon transistor was 55 to 59. Silicon planar technology was 1959. SSI was actually the birth of these mass-produced ICs, which could fit 3 to 30 gates or 100 transistors per chip. It was used for logic gates. It was first built by TI and Intel. And then that was from 1960 in the 1960s. Then we had the MSI medium-sized ones, 30 to 300 gates, around 1,000 transistors per chip, used for multiplexers, counters, decoders, latches, flip-flops. And then we had LSI, 300 to 3,000 gates per chip, or about 1,000 to 20,000 transistors per chip. It was in the 90s, 70s, and the 80s. Then when you got into VLSI, ULSI, and GSI, which are the current technologies, we still use the MSI and LSI, a lot of low-end, electronics like your TV or your toaster or your vacuum cleaner or washer dryer. All of those still use those logic gates today. Even cars, they use a lower technology chips compared to the smartphones. So these are like older generation chips that we use usually in car manufacturing. So VLSIs are more than 3,000 gates per chip, or 20,000 to 100,000 transistors. ULSI is 1 million to 10 million transistors per chip. It's for special processors, virtual reality, smart sensors. And GSI is anything above 10 million transistors, like the latest NVIDIA chip that has 200 billion transistors. A normal iPhone would have 22 to 10 billion transistors. And I think it's useful to show you another video. So there's only one company that builds the devices that prints these. It's called ASML. Let's see if I can find a short video from ASML. I think this is a good one. And
Reverend comes on one of the last major fundraising deadlines before election day. So when I say
at the center of this big factory in the Netherlands, in the midst of a months-long assembly process, there's a revolutionary machine that the whole world has come to rely on.
You can see an EUV machine right behind me.
The size of a city bus, but working with atomic level precision, these EUV lithography machines are the most expensive step in making every advanced microchip that powers the modern digital age. Data centers, cars, and every single iPhone.
We are the only provider on the planet of this critical technology.
These machines are the only way to print minuscule designs on these chips. They cost up to $200 million, and they're only made by a single company, Advanced Semiconductor Materials Lithography, or ASML.
Today, ASML has a monopoly on the fabrication of EUV lithography machines, the most advanced type of lithography equipment that's needed to make every single advanced processor chip that we use today. And this company is one of the most extraordinary organizations in the world. The machines that they produce, each one of them is among the most complicated devices ever made.
In the midst of a chip shortage that's caused back orders of everything from PS5s to Teslas, the need for ASML has never been higher. Its stock has skyrocketed since 2018, while its three main customers, chip makers TSMC, Intel, and Samsung, vie to be front of line for ASML's next breakthrough technology. The price tag for this next machine, which promises to push the boundaries of known physics, is more than $300 million.
It's so expensive that most companies cannot afford it.
While the chip wars rage on, we wanted to find out what's really going on inside the quiet company making the machines that print them all.
The optical part machine that makes EUV possible.
We got a rare tour inside ASML's clean rooms in California and the Netherlands to see how these machines use precision lasers, exploding molten tin, and the smoothest surface in the world to bring our digital age to life. ASML's crucial role on the chip-making stage has brought it wild success over the past few years, making it even more valuable today than Intel, one of the biggest chip makers it supplies.
It's double-digit growth every year, and we're not a startup. You know, we have now 32,000 people.
Peter Wenning has been CEO since 2013, but he joined ASML back in 1999, just 15 years after its humble beginnings. It started as a subsidiary of Dutch electronics giant Philips in 1984, conducting research out of a leaky shed next to a Philips office building in Eindhoven in the Netherlands.
So we're in financial dire straits, so we have no money. We were poor, and because the problems field that were so big, nobody looked at this little outfit out there that was trying to do something crazy, so they neglected us.
Still, in its first year, the company successfully launched a first-of-its-kind machine that used precise rays of light to print tiny designs on silicon to make microchips, a technology known as lithography.
the first lithography tool really looked like a projector. There is basically a reticle, which holds the image that you want to project. Then there is an optical system, which is going to take this image and project it on the wafer.
Semiconductor lithography was invented in a US military lab, and for a long time, through the 1980s, the key lithography firms were American, based in New England.
Chris Miller of Tufts University is writing a book called The Chip War, the fight for the world's most critical technology.
When the industry was getting ready to jump into the early stages of EUV research, none of the US firms were ready to take the plunge on what would be an expensive and risky proposition, whereas ASML was.
By 1988, ASML had 5 US offices with 84 employees, and a new Dutch office that eventually became its headquarters in Veldhoven, where CNBC took a tour earlier this month.
We're walking through the EUV factory, which is about 50,000 square meters of space with 1,500 employees who are working in shifts 7 by 24 to produce 100% of the EUV machines shipped worldwide from this facility.
With a breakthrough machine, ASML started turning a profit and went public on the Amsterdam and New York Stock Exchange in 1995. By the 2000s, ASML was acquiring California tech companies like Silicon Valley Group and various key suppliers like Cymer in San Diego, where we also got an inside look at the clean room where ASML's light source is produced.
So this is actually the nozzle manufacturing area where we actually build the nozzles. This is actually the piece where the tint shoots out of. That's what's going to create your EUV.
EUV refers to extreme ultraviolet, an incredibly short wavelength of light that ASML uses to print smaller, more complex chips. But developing this revolutionary technology was incredibly expensive.
We didn't have the money, so we went out and we found body, which actually was the basis of the way we built the company. So we were forced to be a system architect, and a system integrator.
In 2012, ASML offered about a quarter of its shares to its biggest 3 customers, Intel, Samsung, and Taiwan Semiconductor Manufacturing Co., or TSMC.
They had to accelerate the R&D. And the only way that we do this is to get their largest customers involved. And one way you can make your commitment real is to make them a shareholder.
ASML is a Dutch company, but it's also a Dutch company that relies very heavily on US components, in particular for its machines, and at this point relies also very heavily on one Taiwanese customer for its sales.
TSMC made up nearly 40% of ASML's sales last year. In 2019, the Taiwanese chip maker was the first to deliver high-volume chips made with EUV, a milestone that's kept it at the head of the pack ever since. Its chip technology at least one node ahead of Samsung and Intel.
And it has been TSMC's customers that have gained a lot of benefit, like AMD, NVIDIA, and others. And yeah, you can argue that it has come at the expense of Intel not executing.
Intel is just now producing its first chips with EUV this year, 3 years behind TSMC. But it's made a bold move in hopes of catching up. An early investment to secure the first prototype of ASML's next machine, high numerical aperture.
Hi, Frank.
Hey, Goldie, I'm looking for those reports from yesterday.
To understand why the success of a giant like Intel hinges on ASML, let's take a look at how EUV lithography revolutionized chip making.
When you start breaking down what does it take to make an EUV lithography machine, it's sort of Nobel Prize winning in terms of the engineering involved.
Chips are made from silicon, an abundant element found in rocks and sand that's purified, melted down, then sliced into circular wafers, the surface on which chips are built in a grid formation. Each wafer can have dozens of thin layers, making up billions of transistors that determine what the chips can do. These layers are printed using lithography. Extremely precise rays of light are projected through a mask of the chip design. When the light hits the surface of the wafers, which have been coated with photoresist chemicals, it prints the minuscule designs on each layer at extremely high volumes.
If you think of a typical processor chip in an iPhone, for example, will have over 10 billion transistors on a chip, and Apple will sell 100 million or more iPhones for each model that's rolled out. So you're already talking in numbers that are far bigger than you or I remember how to pronounce.
As the wavelength of the light source in making chips gets narrower and narrower, it gives us the ability to make chips with smaller features, which means the chip is faster, the chip can be smaller, the power consumption of the chip can be lower.
The smallest transistors are more than 10,000 times thinner than a human hair. The designs have gotten so small, ASML had to develop new methods of printing at the very edge of known physics. With the help of customer investments and a consortium of scientists, ASML figured out a way to create large amounts of extreme ultraviolet light with a wavelength so short it's not only invisible to the human eye, it's absorbed by all natural substances, even air. So the entire process has to happen in a vacuum, a first for lithography. At 13.5 nanometers, ASML's EUV wavelength is the size of just 5 DNA strands laid side by side. The previous generation machines used deep ultraviolet light, or DUV, with a wavelength of 193 nanometers. The vast majority of ASML's business, 268 of the 309 machines sold in 2021, still use DUV technology, which is used to print the less advanced chips, which are in shortest supply.
DUV is for anything that is low technology, like a toaster or a refrigerator, or even some of the electronics in your car. Today's iPhone 13 is EUV.
Both DUV and EUV lithography is so advanced, it requires precision down to the atom.
This is an EUV cabin of our clean room, which is 10,000 times cleaner than the outside air. We're wearing these clothing not to protect ourselves from the environment, but we're protecting the machine from the contamination that's created by us.
This tiny thread may look like the strand of a spider web, but it's actually molten tin being shot out at a pressure of 4,000 psi, and it's how the EUV light is created.
This is continuous tin. It never, ever stops.
The tin is streaming through a perfectly calibrated nozzle, which we saw being built in San Diego at a rate of 50,000 droplets per second. A 30 kilowatt carbon dioxide laser hits each droplet twice per second, vaporizing them into plasma. These tiny explosions are what emit photons of EUV light. A huge number of tin explosions need to happen because only about 5% of the photons reach the actual wafer. The light particles are so short they get absorbed by mirrors, the typical method used to precisely aim light through a lens. So ASML partnered with German optics company Zeiss, which makes the flattest surface in the world.
The flatness is really just incredible. If you took a mirror element that is maybe this big and you blew it up to the size of the country that we're in, the biggest bump would only be 1 millimeter across the entire surface of a mirror the size of this country.
EUV light bounces off these groundbreaking Zeiss mirrors until it hits photoresist chemicals on the surface of the silicon wafer to print minuscule designs that make up the chips. The aim needs to be so precise, TSMC says it's equivalent to shining a laser from the moon to hit a coin on the Earth.
So your tin is inside a reservoir here, and then you're firing out this way.
Pete Mayle has been running this clean room for 6 years.
Any kind of defect particle whatsoever is even on the tip of that capillary, it's a fail. We'll remove and start all over again.
And the speed and scale at which this has to happen is staggering. ASML says an EUV machine churns out about 3,000 wafers a day. There can be hundreds of chips on a 300 millimeter wafer and up to 10 billion transistors per chip.
They take extraordinary achievements of engineering and physics, and they're able to replicate these on a mass production scale at a low enough cost where these machines can be used in chip fabs to churn out thousands and millions of chips for the companies that buy them.
A completed EUV machine is actually made up of 7 different modules, each built at one of ASML's 6 manufacturing sites among its 60 total locations around the world, then shipped to and reassembled in Veldhoven for testing. Then it's disassembled again for shipment, which takes 20 trucks and 3 fully loaded 747s. In 2021, ASML sold 42 EUV machines, bringing the grand total it's ever shipped to just about 140.
Hey, since we don't have enough time, I'm going to share the link with you so you can watch it later on. So the next part is the IC packaging, everything after the chip is made. Obviously, you need to put it on a circuit. To be able to do that, you need to put it in the proper packaging. The packagings, you can have different models, like with a metal casing, with resin casing, plastic casing. Depending on what application you're using that, it requires different packaging. The pins also could be like double inline pins, meaning they have pins on both sides, or they could have pins on all 4 sides, or it just could be a linear one line, pins like a voltage regulator, or which looks pretty much like a transistor. The most popular one is the dual inline. So the package type could be dual inline or the small outline, shrunk small outline package and so on. You can read again faster than me. And these are some examples of the IC packaging. Again, you could have pins on all 4 sides or just on 2 sides. We have 2 main methods for all parts, all electronic parts, to assemble them on PCB. We have surface mounted, which is this one over here. And we have the go-through pins. The go-through pins, it goes through the PCB on the other side, we solder it. The mounted surface, the surface mounted ones, you have to actually solder them on the system. And some of them are extremely small. The distance between these pins could be down to 0.1 millimeters, normally 0.5 millimeters, meaning in 1 millimeter, you would have 2 pins. Sometimes it gets so small that you can't solder them by hand. It must be done by machines. But the ones that you're gonna see in the lab and what you're gonna do in the project, so you're gonna have like normal ICs, which are pretty simple too and easy to solder, the go-through ones. But the surface mounted ones, some of them get extremely small and they could only be soldered with a machine. So what is inside these packages? Inside the packages is the chip that you already saw as well. And then we have the resin or plastic. We have the solder balls. We have the substrate, wiring inside. In older generation, mainly these wires were made out of gold. So that's the reason there was a market for, recycling these, and you could get, I think it's from every 200 kilograms of these, you can make like 20 grams of gold, something like that. But it was a profitable business. And so there are a lot of companies that they recycle these ICs because there are gold in them. The reason that we use gold, do you know why we use gold inside? Yes, it's the best conductive that we have is gold and then copper. And that's the reason you don't want to generate any heat. It's a better conductor you have is faster, less heat generating.
Less friction.
Yes. And exactly. Newer generations, they use less copper, they use aluminum, less gold, they use copper, aluminum, different alloys. But still you have some copper in them, especially in the higher end chips. But the lower end, like one that you use in a toaster or car, you usually have less gold in them. Again, different materials are used to building these casings. Some of them, they use ceramic, metal, plastic, different materials. And these are the IC packages. You can see different, like they call it DP pack, DIP. So we have double inline, quad inline, or we call them quad system, which have pins on all 4 sides. We call them QFP. And you may see that some of these also have a metal part attached to them, which looks something like these. Do you know why we use a metal on one side and why we use metal casing? Yes, perfect. These are spots that you can connect a heat sink to it and screw it to them. Usually for power regulators, we need to connect a heat sink. And the reason of some of these casings are made out of, like these transistors are made out of metal, because metal is better in heat dissipation. So we use metal casing for them to be able to cool them down. The fabrication, in the videos, it was already clear. But the basic inside the methods that we build the transistors based on if it's a BJT transistor, FET transistor, or even a MOSFET transistor, or even if you're building a diode or an NPN or a PNP transistor, it could be different. We can build a diode the same way that we can build a transistor We just have to connect 2 of the pins. This is just a demonstration on how an NPN transistor is fabricated in the system. And finally, the advantages and disadvantages of an integrated circuit. Advantages, they are small in size. Due to their small size, they are extremely low power as well. Low power means they are low, they generate lower heat. They don't need a lot of heat dissipation, most of them. They are extremely low cost because you can print a lot of them at the same time, need little to no material. So imagine this, you're gonna get free sand and you put it through this process and you add like a tiny bit of gold and copper and other materials. And then from free sand, you're building something that is more expensive than gold. You have a single chip that is like 300-400, some of them goes for thousands, it's an NVIDIA chip. So you're building gold out of sand, literally, little to no cost for the materials. Like maybe the chip that is $400, the material cost of material, bill of cost of material is like around 20 cents to $1 or something. So from a $1 goes up to $200-300. But again, the process is so complicated. There are capital investment in the devices. So high reliability, facilitates integration of large number of devices, improves the device performance, and the disadvantage is they have limited range and limited power usually, and you can't build an inductor on these, therefore you can't build a transformer on these. So if you want to, you use an inductor, you have to build them separately and connect it to the system. Do you have any questions? No? So for the remaining time, I'm gonna have, the reason I went a little fast was because of the quiz that we want to take. Just give me a second. We're gonna have a small quiz, again, a code quiz. Just gonna take maybe a minute. And yep, that's it. Has everyone joined? Yes. Okay, let's start with the quiz. So what is the most common type of IC? We have one student that hasn't answered yet. Okay, so it's a monolithic. Again, these are time sensitive, the quiz, so if you answer sooner, you're gonna get more points. Sooner, yeah. Okay. So the answer is GSI. Remember this, giga, okay? These have billions of transistors usually in them. Okay, good job. So the labs are gonna start at the third week. I'm gonna put an announcement. For the first 2 weeks, we're not gonna have any labs until we reach a certain point and we cover some material, especially about the op amps. Third week, we're gonna start with the lab, some introductions in the lab, build a simple board. We're using the breadboard simple circuit, and then from there we'll go on. Do you have any questions about the lab or the class or lectures? No. Okay, thank you so much. I will see you next week.